as usual, I decided to go a little slower than planned 5 minutes ago. So more scale calculus today to get ourselves a little more settled, and then the whole sort of splicing situation that we're going to need to deal with nodal curves is for next week. So most notably, I advertised sort of finite dimensions and relation to classical calculus. We're going to want to see how this notion of scale smoothness actually helps when we do a polyfold description of a Gromov-Witten moduli space. And I'll sort of say a little bit about Fredholm theory in this setting. There's already something a little bit non-trivial going on. So back to our guiding example of the simplest possible reparameterization on S1. We had convinced ourselves that that is scale smooth when you look at your CK scales of Banach space completions of C infinity. Now, I would like to see some kind of classical smoothness on, say, finite dimensional submanifolds of the domain. And I can see that by first convincing myself, so this is sort of another fact, if I claimed before that when you map C1 to C0, it's actually differentiable. And if you map CL to C0, it's going to be classically CL. Not just that, you can, so there's a 0 here, you can shift by any k. So if you have a shift between the scales by L, you actually get classically L times continuously differentiable. That's something you can check by hand. It's also something that actually follows from scale smoothness. But let's say we've checked that by hand. We don't actually know about scale smoothness. Now what I would like to now restrict myself to maybe a finite dimensional subdomain of the smooth functions here, and then somehow use the fact that it's secretly CL for all L. So the one of my favorite facts is that when you go to a finite dimensional subdomain, your norms will be all equivalent. Meaning, so norms are equivalent if you have estimates between them. And you can make that in terms of the same constant. So up to a constant C, the norms are the same. So that means not only is convergence the same thing, also differentiability in those norms is the same thing. And so that means it now actually, if I now get to a finite dimensional subspace, so n in the smooth functions is finite dimensional, right, then all these CK norms are equivalent on it. And so then it doesn't, having a shift or not doesn't matter. And so I actually get CL for all L. So if n is finite dimensional, then tau from S1 times n to, I didn't say n is S1 invariant, so this map goes to the smooth functions. And I can now give this my favorite topology, right? for example, the CK topology. Right? And then I can use exactly this fact here to say that this is C infinity classically. And that doesn't depend on which topology I put on the smooth functions. So in finite dimensions, you recover classical smoothness. Since there are CK spaces and classical C somethings, I'll try to write classical something, if I mean that. So, good. So far, so good. Right. So that's one direction, and that is in fact a general fact. So if you have a general scale Banach space and a finite dimensional subspace, then, well, first of all, oh goodness, sorry. What do I want to? Right, this is about scale smoothness. But really secretly what happens here is that S1 times n is a scale submanifold of S1 times E. Right? And the scale structure on S1 times E induces one on S1 times n. And then somehow restrictions of scale smooth maps should be scale smooth with respect to the restricted SC structure. So now the question is, what is that restricted SC structure? Well, we've already seen here all the norms are equivalent, so somehow if you think of the scale just as a completion of the smooth functions in different norms, then the completions are always the same. So you have sort of your scale structure is just sort of constant, always equal to n here. And that is a general fact about scale Banach spaces. So if you have a general scale Banach space, for example, one of these, except now if you ask for this infinity level to be finite dimensional, so reminder, right, infinity is the intersection of all scales. If that's finite dimensional, the claim is that then actually all scales are already equal to E infinity. And by that, well, as spaces, and in fact, that means all the norms need to be equivalent. And that has something to do with this density requirement here. Right? So E infinity needs to be dense in some EK. But if you have a finite dimensional subspace, its closure under a norm is itself, because the restricted norm on this is complete. I mean, we're looking at real vector spaces here. Right? So all finite dimensional real vector spaces are complete. So the closure is in fact the thing itself, right? But that's supposed to be EK, so that proves this equality. And conversely, if even like any one of these injections along the way, if you have some place where this injection is sort of surjective, right? So that means, again, in terms of norms, you want two norms that are equivalent. But not on this, I mean, of course, on the scale, same scale, this is nonsensical. That can only happen if infinity is finite dimensional. And that has something to do with the second bullet here, right? Because, well, let's say maybe k is strictly bigger than j here. So the norms are equivalent, but this embedding needs to be compact, right? And so really, if these are the same spaces and the embedding is compact, then I'm claiming that the identity from ek to ek is a compact map, meaning the unit ball by itself is compact or pre-compact, right? And that is true if and only if that space is finite dimensional. And if ek is finite dimensional, then certainly infinity is finite dimensional. So, little exercises in, I don't know, functional analysis, or even just sort of norms on Banach spaces that say a little bit about what the possible scale structures are. Right? So finite dimensional scale Banach spaces are boring. Yeah. The filtration is constant. And the filtration is constant if and only if it's finite dimensional. So that means that we expect exactly the classical differentiability if and only if we're in finite dimensions. So, and that's usually a good thing. So, before I go sort of, into more properties of scale smoothness, as a review, let me give you the actually useful examples of scale spaces. Right? We had this filtration by CK spaces, but somehow when we do holomorphic curves, we've rarely used Hilda spaces. So what we do want to use is Sobolev spaces, and the nice Sobolev space is when you have a compact domain. So I promote the notion of just putting blackboard boldface on things to denote the sort of canonical scale structure. I think Hofer, Wysotsky, and Sinde haven't caught on to that, but let me introduce my favorite notation here. Right? So this means I want to put a scale structure on the Sobolev space WLP. And I can do that by taking the dense subspaces that have a little bit more differentiability. So it starts at WLP, then it goes to WL plus 1P, and so on. So let's see. On every level, that's a Banach space. Check. Right. We have embeddings that are continuous. Check. They're compact. That's what Sobolev embedding tells me when the domain is compact. So good. And what is E infinity here? Right? So I'm supposed to take the intersection of all Sobolev spaces, and again, so then the Sobolev embedding tells me that they're all smooth, or that a map that's in the intersection has to be smooth. And if it's smooth, it lies in all of these. So, yeah.
Because omega's compact.
Sorry?
Because omega's compact.
Right. Yes. Exactly. So if omega is non-compact, then I was trying to write down a general form and decided that that was just way too complicated. Most non-compact things are non-compact because there's an end. So the main thing that we need to understand is R times a compact thing. That might get attached, as a cylindrical end to another compact piece, but then we could, patch together topologies. So, nice thing is we now have an R component So I would like to do the same thing. Right. Again, these are Banach spaces. We have continuous embeddings. The intersection will be smooth maps. But more than smooth maps, right? When I say LP on this thing, I actually mean finite LP norm. So your smooth maps would have to have finite WLP norm of everything. Still, smooth maps with compact support are dense in all of these, so it's all good, except for the compact embedding. So, Sobolev embeddings are compact only on compact domains. Simply because, I could take a sequence of norm 1 here, that's just a bump function that's centered somewhere on R, and that can run off to infinity. Bounded sequence certainly, has no convergent subsequence. So we need to do something to impose compactness here, and the something is exponential weights, or some kind of weights. Oh boy, I think exponential is a good thing. So you want to put a weight on these, and we usually start our weights with something non-negative. And the important thing is that they strictly go up. So now right. So I want to write down a function. In order to define the weight, I need to write down a function on R that's essentially norm S. Or the absolute value of S, except that's not a terribly smooth function. So I don't really want to multiply nice Sobolev maps with that to get exponential decay. So I'm going to define a smoothened out norm function that just is smooth near 0. That domain here really for the weight doesn't matter. What all that matters is how it behaves at plus minus infinity on R. So with that, I can say that this function is weighted in this weighted Sobolev space if it is in that Sobolev space, but multiplied with this nice exponential decay. So, differently put, a function is in this exponential weighted space if I can multiply it with this badly blowing up function, and after that it's still in, oh boy, did too much copying here, R times omega, of course. Right? So afterwards is still in that space. So, I mean, that's the most efficient way of defining weighted Sobolev spaces. And now I could try again and figure out what E infinity is. And that's a little complicated. So at least the smooth functions with compact support are in all these spaces. And they're also dense in, my Sobolev spaces. Hopefully I know that. The exact identification of E infinity here is going to depend on, whether delta goes to infinity or whether, that converges to something or is, bounded. So I'm going to, in general, allow sort of smooth functions whose derivatives, decay faster than the highest weight here. Well, at least as fast as that. But we have some nice, oh my way. omega has become r times omega, as you can tell. So, yeah, you might have seen analysis for holomorphic curves with weighted Sobolev spaces. Yeah. Here's one other reason why you want weighted Sobolev spaces, because they give you a nice scale structure. So, and there's really nothing, well, yeah. Now you could go and try and prove compactness of the Sobolev embeddings with weights. That's a neat little exercise. That's in fact done in the user's guide, formerly known as user's guide, now polyfolds at a glance or two. So, yeah, pretty much when you work with weighted Sobolev spaces, the sort of wisdom is you do whatever you would want to do on compact domains, in a very large piece. And on the end, you just use the fact that exponentially decaying functions are really integrate to something awfully small. So you can do something totally crude at the ends just because you have that exponential decay. So, meta-analysis. So these are the gadgets that we usually work on, but back to abstract scale Banach spaces and a couple more observations. Right, there was, of course I like to know what my infinity level is, but there's one other good reason why I like to know what my infinity level is. It's namely, so if I have a scale continuous map, right, it maps. Not only is it continuous on arcade, it preserves the level. So that means it also maps the infinity level to the E-infinity level, and is continuous with respect to all the norms that live on there. So in our cases, it would be continuous even with respect to the C-infinity topology. And not just that, but these guys are dense in all the other spaces. So really this determines the map tau uniquely. So that's one reason why it usually is enough to write down, what your operators or maps are on the smooth maps. So.
Is there a simple way to tell if a smooth map from C infinity to C infinity is scale smooth when you give it a scale structure?
Well, yeah. Well, yes. Well, no. But let's see, right? So first of all, you want it scale differentiable, right? Well, essentially, you're just gonna, let me make sure I'm actually answering your question also. This answer is a little bit, more general here. Well, one answer is, of course, you take the canonical extension. If you have this map, if you only define these spaces and that map, right? You could think of a scale structure also, instead of all the Banach spaces, just as different norms on that space. Right? And then those spaces have different canonical completions. But you can also just ask about the scale differentiability and all these conditions with respect of this map with respect to the different norms. And right, that's where it makes sense to try and write out this differentiability here. In terms of the difference quotient, right? So I want the sort of shifted map differentiable for all k, and then I wanted the differential to extend, right? So at a point fk plus 1, I want it to actually be a linear map, not from fk plus 1 to ek, but from fk to ek. That's somehow this notion here. And Right, by the way, so this shifted thing here, that's what we're later on going to call the tangent space, or the scale tangent space to F. So it's something that the tangent space is a bundle that's only defined over the sort of dense subspace of things that are quality 1, not quality 0. But then the fiber is, you know, 1 quality less. So it's another shifted thing. Right. So in terms of difference quotients, right, this means that you need to check something goes to 0 for all k, and that is your favorite difference quotient, which I want to do at x. Right. X plus h, right, minus tau at x, minus your potential derivative applied to h. So classically, you would like to divide this by norm h, and then know that that goes to 0. As norm h goes to 0. So that's and now I need to be precise about the norms, right? So here I want on the f, so this is my, right, h is an f, k plus 1, right? So, is that right? Yeah. But the norm up here is only an ek. Right? So that's just this statement here. Right. This is just rephrasing differentiability. That's something that you could just check when you have the smooth points. You know? And if that works on all the smooth points, and, you know, by continuous extension, that holds on all the Banach spaces, the E's and F's. But if I wanted this equivalence here, I would have to say that also that it extends continuously to Fk, which I think I cannot say in terms of this difference quotient. So equivalence would just mean this, and this d tau needs to be well defined as a map. Right, so yeah, once you have that map, you can convince yourself whether or not it actually maps certain spaces to certain spaces. But usually we're not just asking about differentiability, we're asking about continuous differentiability. And so usually we're asking differentiable and d tau is continuous. So that means I can write SC1 as this difference quotient and d tau being SC0. And that's now something that I can check again just in terms of norms on the smooth elements. And so similarly, SCL means I need this difference quotient to begin with to define what my differential is, and then I've hopefully made sense of SCL minus 1. And I get SCL. So, but that's not the reason I wrote this out. You know, this general fact that I had about the reparametrization map, that, you know, if you allow yourself larger and larger shifts in the scales, you get more and more classical differentiability, is actually a direct consequence of the abstract theory. So if I restrict tau to the appropriate space f k plus L, it actually maps f k plus L to E k classically CL. And that's true for all k. So that follows from scale differentiability L times. It is not all of scale differentiability. So this direction here is wrong. So you need a little bit more than all these shifted differentiabilities. But again, now that we have that fact, we can go through the same argument and restrict ourselves to a finite dimensional subspace and see that on finite dimensional subspaces, I actually map to, well, I directly map to E infinity, and that will be smooth, or classically smooth, no matter which topology I put on E infinity. So I can take any norm here. So again, yeah, not only is scale Banach spaces in finite dimensions exactly boring Banach spaces, also scale smoothness in finite dimensions is exactly classical smoothness. And there's a whole lot of classical differentiability that comes along with scale smoothness. You just have all these shifts in levels that you need to deal with. Right. Which do cause a royal pain once things become nonlinear. So see a little bit of that, hopefully, today. So that's the reminder of all the notions of scale smoothness, and as advertised, the chain rule holds. And just because it's so beautiful, I thought I should actually write down the chain rule. Right? Chain rule says if you have two continuously scale differentiable maps, then their composition is continuously scale differentiable. And, well, you'd like to say that the derivative is the composition of derivatives. And here I need to be careful, right? So here I've mapped the tangent space to F to E. So in order to be able to compose these, I need to actually use something that's a little bit bigger than D. I need sort of the tangent map. So T F should map not just T. Oh goodness, so now I've switched things, right? That tau here was mapping from F to E, and this F is mapping from E to F. So this should map from TE to TF simply by being F in the first component, right, and this differential in the second. And here these tangent spaces again are these shifted things. The first component shifted by 1, and the second isn't. And this is, well, hopefully I said this, I think, last time. If you just had this definition here for scale smoothness that says, if you want C1, you have to shift in level by 1, then the chain rule wouldn't quite work, right? Because you have E, say, E2 to F1 would be C1, and F1 to G0 would also be C1. So you can use your classical chain rule to see that, yeah, the composition is C1. But now the composition goes from E2 to G0, so you had to jump by 2. Right? So somehow this extra condition here, now it's going to get, so this guy here, that should allow you to go directly from, where are we now? E2 is dense inside E1. Right. To sort of be able to extend this C1ness to the closure here. So that's what we'd really like. So, fun, probably not so completely trivial exercise to prove that. Hint, Uwe Wysotsky 10. Textbooks. That they are terribly slow in getting them out, but the advantage is once they do get them out, they are all there with all details. Mostly more details than you care for. So, this is the kind of chain rule that you'd like to see. So it makes sense to think about scale calculus. Of course, there's a whole lot more to develop, you know, to make sort of a full sort of functional analysis based on this. But before we talk about implicit function theorem, let's see how that language actually pans out in the attempted proof of having a Gromov-Witten moduli space. So here's your Gromov-Witten moduli space, just genus 0 maps, no marked points. And our first steps of proving this, of proving that that compactified moduli space can in fact get cut out by a polyfold Fredholm section, were to make those Fredholm sections near smooth curves. So, near a smooth curve, right, we did this whole exercise of fixing mark points and doing slicing conditions. So that gave us in fact, a Hilbert manifold in the base, right, and a d-bar operator that's, a Fredholm section and perfectly smooth. If I'm honest, right? So when I take these 0-1 forms, I actually mean the H2 closure. So far so good. No need for scale calculus here. Right? Then we had the morphism spaces and the structure maps, and the problem was that there was a reparameterization going on, and that is not smooth. So we need to kind of go back to the drawing board. I would like to say this is actually scale smooth. But in order to be able to say scale smooth, I should say that these are not Banach bundles and manifolds, but scale Banach bundles and scale Banach manifolds. And well, that is not terribly bad, right? So what do I mean by that, right? So you take the definition of Banach manifold, and wherever you see Banach, you just put scale in front of it, right? So this means, right? Well, let's exercise our deep knowledge of topology now. It should be a Hausdorff topological space. Right? That is locally homeomorphic to not Banach spaces, but scale Banach spaces. Right? and the transition maps that in this case, yeah, are induced by these homeomorphisms should be not smooth but scale smooth. In particular, goodness, right, if I have a Banach manifold and I put a scale structure on that Banach space that it's modeled on, then the transition maps are actually classically smooth. And if stuff is classically smooth, it's most certainly also scale smooth. So, since we convinced ourselves that this should be an actual smooth manifold, so here we're really not, fearing anything. So everything should be scale smooth. The only thing I didn't actually tell you is what that Banach space is here. So that's a general fact here that would be good to get on the board once. So I can write these things here in terms of exponential maps at my center U. And so then locally at least, well, this is a small thing, right? This is a small open set, so I don't even need to go local. So I can just take the H3 sections of the pullback tangent bundle. I can ask them to be small in my favorite norm. And, well, in order to get this nonlinear condition, I should probably choose a metric in which these are totally geodesic. To define my exponential map, if I do that, then the linearized condition, C of C sitting in the tangent space to HC at the base space U of C. Right, then the linear condition becomes the nonlinear condition under the exponential map. Right, so this is an open subset of a subspace, right? Finite codimension subspace of a Hilbert space for now. And in order to make that a scale Hilbert space, I'm just going to say I'm going to take 3 plus k. I'm going to take this whole thing, k bigger or equal to 0. I'm on a compact domain, so by my previous example, this should be a fine scale Banach space. So now I should be able to actually prove this. To prove that, I should really understand what the morphism space is precisely. So I would like to claim that this is now, in fact, also a scale Banach manifold. But there is this somehow weird pairs, right? It looks a priori like 6 dimensions more than the slice for my chart U, except I have this extra condition that the reparametrized map should satisfy the other slicing conditions. And so that's going to cut down by those 6 dimensions again. So my claim is that locally this actually looks like U times a finite group, namely the stabilizer group of my center chart, little u. And how does that go? So if I have a map V and an element little g here, so where, what is that, U composed with G is U. I would like to make a pair here, right? So problem is that V, which is near U, might not even have a stabilizer, so it might get moved around. And it's not clear that G is going to move the intersection points of V to the right places. So I need to, for this map, I need to find a nearby phi. So the condition here is that phi is approximately equal to G, but, you know, it satisfies this condition, so V composed with phi is in U prime, which means I would like V at phi of Z to lie in the new hyperspaces H prime Z. Those are the slicing conditions here. And that determines phi for me because I can read off, let's see, let me say, V is going to hit this new hypersurface somewhere near the point where U was hitting it. And U, by definition, is hitting it exactly, hold on, is that right? The neighborhood of G of Z? U, that is not quite right. G of Z prime, right. Sorry. All right, so let's see. I need one more piece of preparation here, so I should ask myself. So U composed with G is U. U intersects, right, U lies in the slice for the unprimed hypersurfaces. So, but it will also intersect the primed hypersurfaces someplace. Oh boy. Yeah, and now, geez. Right, so there's, hold on. So I can reparameterize U to go into the U prime slice, but obviously there's, you know, a number of choices because different G's. So I probably need to choose one of them a priori. Right, so, right. So I need to fix U goes to some reparameterized thing. Right, and they're all the same, right? It's like, you know, the stabilizer, of course, doesn't depend on which H prime I have. So, geez. So U inverse of H prime Z. Right, so the problem is that, you know, this now is a tuple of points depending on the order of the stabilizer. And I'm getting combinatorially confused here. So let me pretend for the moment that the stabilizer is just the identity element, which is of course wrong. So let me call that Z prime. And so Right, in fact, I'm going to take that z prime here, so in general, if the stabilizer is non-trivial, I'm going to take that z prime that under the reparametrization to u prime goes to 0, 1, or infinity. So. And so now I'm going to want to, so when I change u to v, I want to read off the one point that, of course, lies in this preimage and also lies near that z prime. And this should be, so that's a unique point, and that needs to be the image of phi. So, upshot here is that phi is determined by three equations, namely for z equal to 0, 1, and infinity. There's some point z prime, which is determined by u, and this point here then is determined by v. So 3 equations in the complex numbers for one automorphism. So that determines this Möbius transformation phi. And and it's going to be near G this way. So that I did that because I now want to actually prove that this here is scale smooth. And for that purpose, I need to somehow understand how this v here, right, that depends on, sorry, phi depends on v. And I need there, so I need to write my transition map here, ideally, sorry, my target map, as some composition of scale smooth maps. So, let's see. So, I want to do this, right, by looking at this identification, right? So, I'm giving this the scale smooth structure that I get from this product here. So I want to think of really u times the stabilizer of u as the scale smooth structure here. And then I want to map v comma g. And first I'm going to read off those points. So I'm going to keep v in mind, and I'm going to read off these points, and there's probably, oh goodness. These points here have something to do with G also, which has gotten a little fuzzy now. From there, I can determine V and phi, and from there, I can make my reparametrization. So that means, right, as a map, first I go to the slice times, 3 points in P1. From there I go to the slice times Möbius transformations, and then I reparametrize. So now let's see. So this map here is scale smooth, similar to the S1 parameterization. Right? This map here is just, is the identity on the infinite dimensional thing. And on the finite dimensional part, it just takes 3 points in P1 and makes the modulus transformation that maps those two as standard points. So that's perfectly smooth. And here, it's a little bit funky, right? So I need to sort of look at pre-images. So, as long as if V is very differentiable, then this map that reads off where it intersects something is very differentiable. So this here will be CL, I guess, in the topology H3 plus L on U, because then things are embedded into CL maps V. But that in particular will be scale smooth. Right. And I don't have to worry anymore because somehow the interesting part of this map goes to finite dimensions here. So the shift, I let me not try the same one here. So, understanding this fact, if you write things out, you see that this will be scale smooth. You can also get it, if you go to some sort of dense subset here, you can get it as different. So from here just to there, you can get the thing as differentiable as you want. It's just that this map is the one that really fails to be differentiable in any infinite dimensional setting. So what people often do is, sort of get this as differentiable as you want, and then once you have that, you somehow need to argue that you can, or whatever setting you're in, you can just talk about finite dimensional submanifolds here, and then that was scale smooth. So, that's the semi-rigorous proof now that we actually have scale smooth transition maps between scale Fredholm sections. So, well, I haven't, it's a scale smooth section. I haven't told you really what Fredholm means yet. And of course, the other thing that I totally haven't done yet is any of this theory once you get to nodal curves. But that's for next week. So I want to get closer to sort of the meaning of Fredholmness, and I'm going to do that from observing that, the obvious operator that we want to look at here, the d-bar operator, is in fact a nonlinear elliptic operator. So, and when I first saw scale calculus, it was like sort of this moment of sitting in the back of a steamy lecture room, and you see all these sort of crazy definitions, and you wonder what are they about. And I mean, reparameterizations didn't make a whole lot of sense to me then, but to me this was just like, oh my god, this is the right language to talk about elliptic operators. So, because I had worked on Uhlenbeck compactness, and somehow Karen Uhlenbeck was proving a lot of things by saying things like elliptic operators are well defined on all Sobolev scales at the same time. So what does that mean? What that means, for example, is, right, so if you look at the Cauchy-Riemann operator, so this is now the totally linear operator. Right? I want to talk about linear things first. And I want to take a compact domain here, and because I want to just write this in very simple terms, I took the tutorials. Right? And, maps smooth maps to smooth maps, but it also maps WK plus 1 P maps to WK P. And really, your choice of K and P here doesn't matter. You're going to get, the same Fredholm index, the same kind of theory, the same. It's going to be Fredholm in all or none of them. Well, as long as P is not 1 or infinity. And so, in terms of scales, it's very easy to say what all these things mean. First order elliptic regularity. And not just Fredholm in 1, but in all. So, so first order here really means I could say that D is in fact an SC0 operator between some scale Banach spaces. Namely, right? E is this for all k bigger equal to 0, and F is this for all k bigger equal to 0. So if I restrict D on each one of these, it's a continuous map, but in linear operators, this means it's a bounded operator. On each scale. All right. And first order here means really this F here is secretly is E1. Right, so that 1 here is first order, namely it's E but shifted by, oh goodness. That's the wrong way, sorry. So this first order is, I've shifted the other way, right? So this here is F1. Starts with the one level up within F, right? Okay, right. So once I have one bound for the Cauchy-Riemann operator, I get that on all Sobolev scales. And similarly, I can now write elliptic regularity in terms of this. Well, that's just a rewriting. So, right, elliptic regularity says if du is w kp, then u, right, these are some first derivatives of u, and elliptic regularity says that actually all first derivatives have that differentiability, so u is in wk plus 1p. But in my world now, this here is fk, and that is ek. So not only does D map ek to fk, it also, well, it doesn't quite have an inverse, but if the image is in fk, the preimage actually is in ek. So and that's true again at all scales at the same time. And because that looks so beautiful, you can just give this a name in scale calculus, and since it has to do with elliptic regularity, we call an operator like this regularizing. It regularizes because if the image is in good quality, then the preimage was in good quality point. All right, and I should not give my lemma away. So Now I could also go ahead and state the fact that these things are Fredholm in all K and P's, but instead let me just say that they're Fredholm on W1P to LP. Alright, so this is just from E0 to F0 Fredholm. Well, i.e., right, it has kernel, finite dimensional, and co-kernel. Finite dimensional. You not write image D, and you write D of E0. One thing I can also observe is that because it's regularizing, right, the kernel says du is 0, so it's actually an F infinity. So regularizing then says that u needs to be an E infinity. It's like holomorphic curves are smooth. So we have a finite dimensional kernel that already lies in E infinity, so that kernel is obviously the same no matter where I started here. Question is whether the co-kernel is also the same no matter to which level I'm at, and that's where you can convince yourself of that separately for every elliptic operator that you want, but you could also prove the following little lemma. Okay. It says if you have one of these SC0 operators that is regularizing and that's Fredholm on one level, right? So that satisfies elliptic regularity, and you check, for an elliptic operator, the elliptic estimates then prove Fredholmness, right? But these two facts together with some fun functional analysis actually prove that your operator is scale Fredholm in the following sense. So that sense is, right, so this is the definition that says it's an isomorphism up to infinite dimensions split off in domain and target. So I would like to split off the kernel, right, which lies in E infinity. And there should be a complement and a direct sum, but no, that direct sum should somehow be meaningful on all levels. Right? So I would like for all k, ek to be the sum of, the kernel that sits in all of these direct sum with the k level of this sort of scale subspace. So that's sort of the definition of scale direct sum. It should be two scale subspaces, so that you have direct sum on every level. And you want to play the same game in the image, so you want to write fk as the image of d in that level, which by regularizing property is exactly ek, or d on ek. And you want that to be a direct sum with C. And in order for C to be the same, it makes sense on all of these levels, you just like C to be an F infinity. So I don't just want a complement of the kernel, I want a scale complement. And I don't just want a complement of the image, I want a complement in the smooth points. And then I restrict this, and I should get an isomorphism for all k, right? So D on each of these complements now should be an isomorphism between the image within Fk. So scale isomorphism means it should be an isomorphism with respect to these norms. In particular, right, so if you now just read this on a fixed level, this implies that D restricted to Ek from Ek to Fk is Fredholm. It's not just Fredholm, it has the same kernel in it, and it has the same co-kernel, so it has the same index. And if you want to go more into sort of determinant line bundles, it actually has the same determinant, right, because kernel and co-kernel are the same. So the upshot is, well, elliptic operators should be scale Fredholm. And even in general, if you don't know that it's elliptic, somehow you don't have to prove that much beyond your standard Fredholm property to get scale Fredholm properties. Unfortunately, that is only the case in linear operators. So here's a dream, right? So I would like awfully to take the implicit function theorem, in Banach spaces, right? Which is exactly this one. Oops. And make a copy of it. And apply my previous sort of cooking recipe of just putting SC in front of all occurrence of Banach spaces. So I'd like to get an implicit function theorem that gives me actual submanifolds in, well, E infinity, maybe, because that's what we're expecting. Nice, finite dimensional scale calculus to be calculus again. So we should start with SC Banach spaces. We probably want our map to be SC infinity. Well, and so we should ask for Fredholmness. We could ask our linearized operators to be SC Fredholm. And transversality still means they're surjective. Well, that's a dream. So can we prove that we're getting finite dimensional smooth submanifolds? So, well, let's see. Well, there's one place where that already sort of gets fishy. You'd like to make a local chart near some point. And I would really rather not have to linearize at points that are not E infinity. So I'd like to a priori know that my zero set is in E infinity. Otherwise, this makes no sense. So, but I can ask my nonlinear map to be regularizing in the same sense that the linear maps were regularizing, that the zero sets are automatically in the infinity level. So far so good. And then I should try and do Newton iteration to find the local chart. Right? So I'm in E infinity now with my kernel at E. And if I have an vector here, I should add x to that vector and then some correction term xi that's going to come from the Newton iteration. So Newton iteration is going to ask, well, we're trying to find xi so that that's in the zero set. And there should be a unique solution if we're restricting ourselves to the complement of our kernel. For complement. So the setup of the Newton iteration is, let's see. I start with xi equal to 0, and then the next xi I get by adding the right inverse, or subtracting, oops, the right inverse applied to the value at the previous one. So Q here should be, let's see, what do I have? D, E, F. Maps this complement as a scale space isomorphically to the image of D. And Q should be the sort of inverse that there is on every scale. So Q is a bounded SC operator. So it's not so bad as a setup to begin with. Right, note in particular that if I started with xi that's 0, that's obviously in the infinity level. What happens here is that everything is in the infinity level here. F maps the infinity level to the infinity level, and then Q is a scale operator, so this is in the infinity level. So I stay in the infinity level. I should actually find a smooth solution. But the problem is, when I now try to write out my iteration, right? So this should converge. So I'd like to get Cn. I'd like to get an estimate for norm Cn minus norm Cn minus 1. And oh boy, no. This should be iterative. So Cn plus 1 minus norm minus Cn. So that is right. I can bound this. That's exactly this Q here in terms of the operator norm of Q times F at E plus X plus Cn. Now let me see. So let's say I want to prove convergence in the EK norm, then I can put the FK here because this guy is bounded as a map from FK to EK. So far everything is good, except now I need to bound this guy. And that's where I'm going to use my difference quotient. Now that's where things are going to go bad. Right. So that is part of the difference quotient. So this guy sits here. So I need to pull those two terms out here. So far so good. And then there's a difference quotient times something. One of the problems is that I've now, this bounds the ek norm of that difference in terms of the ek plus 1 norm of the previous difference. And similar things, well, here, ideally you'd like to keep this one small and have this also bounded in terms of some norm Cn minus Cn minus 1. But again, there's an fk here. Continuity of the differential only holds, when you're shifting by 1. So a priori you're just getting the ek plus 1 here. So unless you're on a finite dimensional space with your Newton iteration, on which all these norms are equivalent, you're not getting an iterative sort of estimate here. So this shift here is no good. And that means we need either more differentiability, right, so that we can undo this shift, or we need, maybe without the differentiability, some kind of contraction property that we can throw into the Newton iteration to make this work. And that's the motivation of the nonlinear definition of Fredholm properties, which I'm going to save apparently for next week. But, well, you could, so pretty much the definition of nonlinear Fredholm in scale calculus is, the notion of SC Fredholm here for which the implicit function theorem holds. And then, well, one could try and prove that there is a unique notion for that, for which that's true. But there's certainly an obvious notion for which it's true. I'll give you that next time, and then we're going to go do even more funky stuff, near nodal curves, where the notion of Fredholmness is going to get even more challenging. But again, you sort of use the definition by your dream. You need to define Fredholmness so that the implicit function theorem holds.